Okay, we're going to be talking about damping factors of trig functions today and just some other little odds and end ideas just to kind of wrap up this unit 4.6 day. So first of all, we've got some pictures here that go along with the equation y equals quantity x squared plus 5 times the cosine of 6x, and then f of x equals 2 to the negative x power times sine of 4x. So I've got the pictures there, and you can see that these pictures have a damping effect, meaning that as time goes on, depending upon which direction you're going, the graph gets smaller in the vertical direction. So there's different types of damping. So if you look at this first one right here, the x squared plus 5, as you can see, this graph right here is kind of getting smaller as x approaches 0, y goes to 0. That's kind of what's happening. Same in both directions. So this is kind of dampening to 0. It's just getting closer. As it gets closer and closer to the origin, the y value gets closer and closer to 0. The damping factor is what's in the amplitude spot. So it's this part of the equation right here, x squared plus 5. That's the damping factor. So whatever's in the amplitude spot is what's going to cause a damping effect. And in order for it to cause some kind of a damping effect, in that spot there needs to be a variable. If it was just a number, if it was just like 5 cosine 6x, the only thing, it won't cause any damping of the graph. The only thing the 5 does is just change the amplitude to go up 5 and down to 5. So there won't be any damping effect. So if you want the damping effect, you have to have a variable in the amplitude spot. So then if you look down here on the one on the bottom, once again, you can see this is the damping factor right here, 2 to the negative x. That's the damping factor. How does that affect the graph of sine of 4x? Well, as x goes to infinity, so as I keep moving to infinity, what happens to the y value? It also goes to 0. So on this one, as x goes to infinity, y goes to 0. Up here, as x goes to 0, y also goes to 0. Okay. All right. So here we go. Here's some equations, and it says name the damping factor. Now, we could go ahead and graph all of these on our graphing calculator if we want to see what they look like. But just to name the damping factor, I'm going to look right here in the amplitude spot. So this one is an x, this one's an e to the negative x. This one is a 3, so there really isn't a damping factor. And this one is a negative 2x. Okay, let's just pull up our graphing calculator and kind of just see what those look like so you can see, yep, that's true. So on this first one, x sine x, I'm going to go y equals x, oops, x, what's happening here? X sine x, we'll hit graph. And you can see this one as x approaches, as x goes to 0 from both sides, from negative infinity to positive infinity in the x direction, the y values approach to 0. So that's what's happening on that one. But our damping factor was just x. So let's put that here. Okay, let's do the next one. So this one, we're going to have, clear that out, e to the negative x power and sine 3x. And then we're going to hit graph. And then this one you can see as x goes to positive infinity. On this one, how's it damping? As x goes to positive infinity, as you keep moving right, the y goes to 0. So, and the damping factor on that was e to the negative x. Okay, so now let's look at this next one. I said it didn't have any damping effect. Let's just see what happens. It's just 3 cosine 2x. There isn't a variable in the amplitude spot, it's just a number. So you can see it stays constant. So there is no damping effect on this one. So this one is a none. It stays constant because there's no variable in the amplitude spot. Remember, the variables change, and so that's what's causing the change. 3 is a constant number, so that would be no change. Okay, and let's look at the last one. So clear, negative 2x cosine of x. Let's graph that one. So that one looks like as x goes to 0, y also goes to 0. So your damping factor, so this one is x goes to 0, y goes to 0. So the damping is at the origin on this one. And the damping factor is a negative 2x. Okay, so remember your damping factor is always located in the amplitude spot, and there has to be a variable there in order for it to have a damping effect. Otherwise, it just stays constant. Okay, this says use a graph to solve the equation on the interval from negative 2 pi to positive 2 pi. So I'm going to show you both ways. I think in the book it says to solve it and then to use the graphing calculator to prove what you've done. So basically what you're going to want to have is a unit circle handy. So you want your unit circle handy. And they want to know where the tangent x is equal to square root of 3. Okay, now up here what they're saying when they say negative 2 pi to positive 2 pi, that means that you rotate all the way around the unit circle in the positive direction and you rotate all around the unit circle in the negative direction. So you go both directions looking for your answers. So what I'm looking for is where the tangent is equal to the square root of 3. Now, in my graphing calculator over here, you can see that I have put in, this isn't a decimal, but this is negative 2 pi, and this is positive 2 pi for my window. So you can see that I have everything the way it should be, and it looks graphically like there's 1, 2, 3, 4 answers. Now, if you're looking on the graphing part here, this is 0, and to here is positive 2 pi. So the solutions that are in here are when we go from 0 to 2 pi, and now the solutions that go on this side are when you go from 0 to negative 2 pi. So you've got two solutions when you go positive and two solutions when you go negative. So let's see how that looks on the unit circle. If you're trying to find out where the tangent is the square root of 3, remember you're looking tangent, there's all kinds of definitions for tangent. We can say that's opposite over adjacent. We can call it y over x. We can call it sine over cosine. It doesn't matter. When you come over here to your ordered pairs, however you look at them, if you're looking at x, y, cosine, sine, adjacent, opposite, it doesn't matter. What's happening here is I'm looking for the square root of 3 over 1 because that's what I want, square root of 3 over 1. Now because in the unit circle the fractions are all divided by 2, I'm kind of just going to disregard the bottom part of the fraction. So this is the one I'm looking for, square root of 3 over 1. So one of my answers then, now because they gave me the domain in radians, you're going to want to give your answer in radians. So right now it would be right here at 60 degrees or pi over 3. So I bet that answer right there is pi over 3. Okay, let's keep rotating counterclockwise in a positive direction until we can find the next one. This would be a square root of 3 over negative 1, so that'd be minus the square root of 3. So I bet we're going to be down here where it says negative square root of 3 right here, negative square root of 3 divided by negative 1. That'll be positive. So that answer is going to be 4 pi over 3. Which is going to be this number right here, 4 pi over 3. Okay, that was rotating, and then we just finished rotating to here, and we got all the answers. That was rotating in the positive direction. Now we're going to rotate in the negative direction. So I'm going to start here, and I'm going to come to this spot right here. Okay, that spot right there. And I'm not going to write 4 pi over 3. I'm going to write what? Negative 2 pi over 3. So this is negative 2 pi over 3. And that would be this one right here, negative 2 pi over 3. And then we keep rotating around till we find the other spot, which was right here. Okay. And that would be what? That would be a negative 5 pi over 3. And that's what this value right here would be, a negative 5 pi over 3. So you can use your unit circle to solve that, and then you could just type it in your graphing calculator to check to make sure you have the right answers. Okay, let's do the next one, secant of 2. So I'm remembering that secant is the reciprocal of cosine. So on my unit circle, basically what I'm looking for is where the cosine equals 1/2. So as I go around, once again, as I go around in the positive direction, looks like I'm going to get the same answer set right here. I got cosine is 1/2 right here at pi over 3. So that's going to be one of my answers, pi over 3. Okay, I'm going to keep rotating until I get another positive 1/2 for my cosine, which is going to put me right here. Okay, and that's a positive 5 pi over 3. Okay, now we're going to do the same thing, but we're going to rotate in the negative direction. So if I start here and I go to this spot, that's going to be a negative pi over 3. And keep rotating until we get to here where it's a half, and that's going to be a negative 5 pi over 3. Okay, so let's see what that would look like if we were to graph it. So let's go ahead and pull up our graphing calculator. And here I'm going to put in secant x. And remember, secant is 1 over the cosine. So I'm going to go 1 divided by cosine x. And then I want it to be equal to 2. So then I'm going to put 2. Then I'm going to hit graph. And let's see what my window it looks like. Okay, so I'm further out than negative 2 pi, so I'm going to change this to negative 2 pi. And I'm going to go to positive 2 pi. Oops. Now let's hit graph again. And we can see our answers. We've got 1, 2, 3, 4. And that's what we found when we went around the unit circle. So it's matching. So you can use your unit circle and you can use your graphing calculator to show that that's equivalent. Okay. All right. So now this one says determine if the function is even, odd, or neither. So there's our definition of even and odd functions. If a function is even, when you substitute in a negative x for your input value, you get exactly the same function out. And if it's odd, when you substitute in negative x, you get exactly opposite out. So that's what that little blue box is saying for odd and even. Graphically, sometimes it's easier to tell graphically if they're odd, even, or neither. So if they're odd, the symmetry is with the origin. And if they're even, the symmetry is with the y-axis. Okay, so we're going to go through and show this algebraically as well as graphically. So if you looked at this graphically, This one is symmetric. The first one, cosecant x, is odd. It's symmetric with the origin. Here's the first. If I took this and I just reflected it over the y-axis, it would come over here like this. Okay, but then so that's reflecting over the y-axis. Now if you took this piece right here and reflected it over the x-axis, then you would end up with this branch right here. So that's odd. So graphically looking at it, that's symmetry with the origin. It has to reflect over the both x and the y-axis. So that's odd. If you were looking at, I don't know if you remember earlier in the chapter where we talked about even and odd identities. And we talked about cosecant x. This is on g of x equals cosecant x. So what would happen if the test is what happens if you put in a negative x. So if you put a negative x right there, what is that equivalent to? Well, we could prove that from the unit circle, that if you go this direction or this direction, depending upon which way you're rotating, that they're exactly opposite. So remember, cosecant is the reciprocal of the sine, and in this quadrant, the sine is positive, and in this quadrant, the sine is negative. So if you're rotating the same amount but in opposite directions, the sine values are always going to be opposite. So this is equivalent to this. Whatever the cosecant is, then you just take the opposite sign. So is that exactly opposite? Sure. If we come back up here and we look at it, here's f of x is cosecant x, right? That's what's given. And so if I put that negative sign out in front, now you have exactly the opposite. So they're exactly opposite. When I put this one in, I put a negative x in, I get negative cosecant x. Those are opposite. So algebraically, that's showing that it's odd. Okay, let's look at the middle one. Graphically, it looks like to me this is even. It looks like it has symmetry right here with the y-axis. I could just fold those two pieces right over onto themselves, and that would be symmetrical. So graphically, that looks like it's an even function. Okay, so how would we prove that algebraically? Well, we remember our test is we have to substitute in a negative x. So I come over here and I put a negative x everywhere I see an x, so it's going to be x squared minus, and then secant of negative x. Okay, so when we put in a negative x, algebraically speaking, a negative x raised to the second power, that still stays positive x squared, right? A negative raised to the second power is still a positive. Negative times negative is positive, so that's x squared. So this one right here, secant, we've got to know what this one is equivalent to. Secant of a negative x. Well, secant of negative x is the same thing as secant. Okay, so remember, secant's the reciprocal of the cosine. So what does that mean? That means that when you're rotating positive direction and negative direction the same distance, you're just going positive one way, negative one the other way, what happens to the cosine? The cosine is the same value. It doesn't change. Even though whatever this angle is that I've drawn, I don't have a number value for it. I ended up in the second and the third quadrant. The cosine in the second quadrant is negative, and the cosine in the third quadrant is negative. So they end up always being the same. So secant of a negative x is the same thing as secant. That's your even and odd identities. And so the subtraction sign just stays right there. So now compare what we had written right here, x squared, this right here, x squared minus secant x looks like the original problem, so that means that it's even. When we put in a negative x, we got the original function out. So that's even. Okay, so last one. If I look at this graphically, I'm thinking this looks odd, If I take this piece right here and I reflect it over the y, it looks like this. And if I reflect it down, it looks like this. So graphically speaking, this looks like an odd function. It has odd symmetry. Or symmetry, not odd symmetry, sorry. Symmetry with the origin, but it's an odd function. Well, if we want to test that algebraically, our test is, I'm going to erase this piece right here. We're going to substitute in a negative x. And we're going to get negative x squared times the cotangent of negative x. All right. So let's see what happens here. A negative x raised to the second power will always be a positive x squared. And what about cotangent of a negative x? What happens there with that one? Does that one turn out to be the exact, like, so what we're asking is if I start here and I rotate this way and I rotate that way, do I get the same thing every time? You don't. Cotangent's going to be exactly opposite. So what that's saying is this piece right here is equivalent. So it's going to look like this. So that's the same thing as saying cotangent of x. We want that x to be a positive variable right there. And this is all multiplying, so this is going to be a negative, oops, let's get my equal sign in there. A negative x squared times cotangent of x. Okay, so let's look at that. How does that compare? So when I put in a negative x, did I get g of x out? I don't think I did. I think I got the opposite of g of x out, so that means it's odd. So you can go algebraically and geometrically. You got to know how to do both. I think in the book it asks you to do it algebraically and then use your graphing calculator to confirm. So that means you can look at it and see geometrically what the symmetry is for odd and even. And if it's neither one of those on the symmetry, then it's a neither. So they don't always have to be odd or even. It may not work and it might be neither. Okay, so this one says graph the function and describe the behavior of the function as x approaches 0. So you can approach 0 from both directions. So x can approach 0 this way and x can approach 0 this way. Now I typed this picture right here is this typed into the graphing calculator. Now you cannot disregard this statement right here, x is greater than 0. X is greater than 0 is telling you that you have to discount this side of the graph. We can only use this side of the graph where x is greater than 0. That's important because in order to describe what's happening, we'd have to do both directions. We'd have to say x coming from the positive or x coming from the negative direction. So now that we're only working with one side of the graph and we want to write the behavior, well, this is what we can say. As x, so as I get closer to 0, as x approaches 0, y is increasing. It's getting higher and higher, so it's going to positive infinity. Okay, so that little domain restriction was really important so we would know what side of the graph we were working on. If we didn't have that domain restriction, we'd have to have two statements because on the left-hand side, as x goes to 0, y goes to negative infinity. So you have to be able to describe both sides. So that domain restriction told us we only needed the right-hand side of the graph. Now, if you look at the bottom one, there's no domain restriction on this. So once again, x can come this direction or this direction, but I don't think it really matters what direction. As x goes to 0, what's happening to the y value? If you look right here, it's kind of bouncing, it's getting to 0. It gets smaller and smaller and smaller to 0. So as x goes to 0, y goes to 0. So you're just describing what's happening in behavior, what's happening at that point on the graph. Okay, we're done.